For these next two examples, we are going to look at how completing the square is helpful in integration. So this one right here is J, part J from, or example J from 6.9. So as it is, it's not a trig inverse function the way it's written. It's also, or derivative, it's also not like a natural log. It's not 1 over u du because I don't have any x's in my numerator. However, I can complete the square here and I can write this as 1 over, okay, so I need x squared minus 4x. So to get a 4x as my middle term, that's going to be x minus 2 squared. But x minus 2 squared is actually x squared minus 4x plus 4. I have a plus 7. That means there's 3 more left over there that aren't getting used up in this right here. So that's x squared minus 4x. Oh, no, I'm sorry. It's in its completed square form, x minus 2 squared plus 3 dx, okay? If you need more help completing the square, there are hundreds of videos, I'm sure, or let me know and I can go over it with you. And from here, now we can see that this is a tangent inverse form where this is our u squared, so u is equal to x minus 2, and this is a squared, so a is root 3. And so my formula, oh, let me check, du is just 1 dx, so I don't need to manipulate the numerator. So then my form for the antiderivative is 1 over a, so 1 over root 3 times inverse tangent of u over a, so x minus 2 over root 3 plus c. Okay, one more example here, with this, completing the square, okay, so I'm going to start by making that negative, putting the x squared in front and factoring out the negative. So this is going to be x squared minus 3x and then something, okay? So that's going to be x minus 3 halves squared, but x minus 3 halves is actually x squared minus 3x plus 9 over 4. Okay, so that means there is an additional 9 over 4 inside here that was not present originally. Okay, so I need to take that 9 over 4 back out. Okay, and then distributing my negative back, I'm going to have a negative on this and a positive 9/4. Now, if my 9/4, the constant is the positive part, based on my antiderivative formulas, that needs to come first, okay? And then I'll be looking for a sine inverse as opposed to a secant inverse. All right, so then this becomes, I'm going to come down a little bit here. This becomes the integral of 1 over root, okay, so then I have 9 over 4 is the positive part, and then minus the quantity x minus 3 halves squared, and then dx, okay? And I can always expand this back and multiply it and see if I get what I started with. Okay, so from here, my u is x minus 3 halves. My a is the square root of this, so 3 halves. And my du is just 1 dx, so I don't need to manipulate anything here. So this is a sine inverse derivative where I have the constant first minus the variable term under the radical. And so my formula then is sine inverse of u over a. So that's going to be x minus 3 halves. Actually, I don't need those. X minus 3 halves over 3 halves. I'm going to clean that up. Plus c, which is sine inverse of multiplying the top by 2. I get 2x minus 3 over 3 plus c. Okay, and then for these last couple, here we are looking for a way to algebraically manipulate. This is not something that will probably show up on an AP test, but it is kind of just another method for integrating. Right now, this is not a tangent inverse because I can't say, well, you know, this is my u squared, so u is e to the x over 2 or anything like that, because I wouldn't have a du. It's also not a natural log because, once again, my du wouldn't be present. What I can do, though, is I can both add and subtract something. So I can't just change it, but if I add a net amount of 0, if I can add and subtract something that allows me to split this into two different fractions that are each able to be integrated, then I can do that. So what I'm looking at is I see e to the x plus 1 in my denominator. If I had an e to the x added in my numerator up here, order doesn't matter with addition, this would reduce to 1. But if I add e to the x, I also need to subtract e to the x. Okay, so this is what I have now. I have 1 plus e to the x over e to the x plus 1, and then minus e to the x over e to the x plus 1 dx. Okay, and you might be thinking, well, how is this better than what we had before? Well, this one reduces to just a 1. Okay, so integral of 1 minus, and then this I can do an easy u substitution. So we can say the denominator here is u, so du is e to the x dx, which is what is present. So this is minus 1 over u. Let's split this into two integrals. So 1d, because that one is a dx. This fraction is with respect to x. So 1 dx minus the integral of 1 over u du. Okay? I can't substitute over here. Like, this is not a du because there was no, when I reduced this to just a 1, there was no e to the x attached to that. Okay? All right, so then our antiderivative is x minus natural log of u, so natural log of e to the x plus 1. And actually, I could use parentheses there because that can't be negative, but that doesn't matter. And then plus c. Okay? Last one here. I'm not going to do long division or anything like that because I have a higher degree in my denominator. And it's also completing the square is not going to be very helpful. Let's see, because I would have x minus 1 squared, so that's x squared minus 2x plus 1. Then I'd have an additional plus 2. But my derivative here, if this is my tangent inverse, my derivative of 2x minus 1 is not going to work in the numerator. So I am going to need to manipulate a little bit, and then I will be completing the square. But I'm going to change this, and I'm going to, excuse me, I'm going to treat this as though this was my u, because if that's u, then my du would be 2x minus 2 dx, almost what I have here. So if I can subtract 1, that gives me 2x minus 2, but then I'm also going to need to add 1. So that, again, that's that adding 0. I'm adding two things that cancel each other out. So now I can split this as two different fractions, or two different integrals. So I can write it as 2x minus 2 over x squared minus 2x plus 3, and that's going to give me my 1 over u du, okay? And then plus the integral of 1 over, and I'm going to go ahead and use my completed square form because I already did that, so x minus 1 squared plus 2 dx, okay? So then this first one is a 1 over u du. This one over here is a tangent inverse derivative. Okay, so then integral of 1 over u du, I already know that my substitution matches, so that's going to be natural log of absolute value x squared minus 2x plus 3 plus, and then this is a tangent inverse form where u is x minus 1, du is just 1 dx, so I don't have to change anything there, and then a is root 2. So this is 1 over root 2 times tangent inverse of u over a, so x minus 1 over root 2 plus c.